Okay, I have selected problem 1629 from the textbook to illustrate an example of timber beam design. So this specifically is a joist problem, which really just means that we have a series of beams repeated and equally spaced here. This really only requires a slight additional step here to find the load. So we are given a 40 pounds per square foot dead load. It's just kind of formatted strangely here in my ebook, so I'll just write the units up here. Pounds per square foot dead load and 12 pounds per square foot live load. So if we add those together, we've got 40 and 12 is a total of 52 pounds per square foot. The spacing of our joists is 16 inches. So the tributary width of one of our joists is equal to the spacing, or 16 inches. So the uniformly distributed load on our joist is equal to 52 pounds per square foot and I'm going to convert that into square inches or pounds per square inch. So for every 1 square foot there are 144 square inches. And so that will get us into pounds per square inch. And then I multiply that by the spacing of the joist, or the tributary width, of 16 inches to get a uniformly distributed load of 5.78. And the units I'm left with are pounds per inch. Okay, so if I were to draw a beam diagram from the side, I've got a simply supported beam with a uniformly distributed load, and that uniformly distributed load is 5.78 pounds per inch. Okay, so now it becomes just like a typical beam design problem. I've got my simply supported beam, I've got a uniformly distributed load. I can start to design based on the allowable stresses. So I have hem fir, so I need to look up in the appendix what the allowable bending stress of hem fir is. So I've got appendix F right here. We're dealing with hem fir. So we have FB, an allowable bending stress of 1000 psi. And what else are we going to need? The allowable shear stress is 150. And the modulus of elasticity is 1400. So let me write that down. FB, allowable bending stress, for our hem fir is 1000 psi. Our allowable shear stress is 150 psi. The modulus of elasticity is 1400 psi. Okay, so let's start by calculating the moment. So what moment is going to be caused by this uniformly distributed load? It is uniformly distributed, so the formula for that is WL squared over 8. Again, if you don't have that memorized, it can be found in Appendix H. But since it's the most common type of support and loading condition, I happen to have it memorized. So our W is 5.78, and I've got it in pounds per inch, which means my unit of length here also needs to be in inches. So the span length of one of these joists was 12 feet. So from one support to the other, the way we're looking at this, the length of the joist, the span length is 12 feet. So 12 feet times 12 inches per foot is going to give me 144 inches. That's how long it is in inches. You absolutely need to make sure that you use consistent units. That is by far the most commonly made mistake in these types of problems. So I've got my distributed load times the length squared. Don't forget to square it. That's another common mistake. Divided by 8. So our moment being applied to our beam is 14,982 pound inches is the moment that's being applied by our dead and live loads on these joists. Each joist is experiencing this much moment. So we now have to determine what type of section modulus we need to resist this moment. So our formula for bending stress is moment divided by section modulus. So if we want to solve for section modulus is equal to the moment divided by the allowable bending stress. So our moment is 14,982 pound inches, and the allowable bending stress was 1,000 psi. So I've got pounds, pounds, inches, inches. It's really important to make sure those units agree. And so this is going to give us 14.982 inches to the third power. Or we could just round that up, I suppose, to say 15 inches to the third is what we're going to need from our chosen timber. So I look at the Appendix E. Let's look at Appendix E. And since this is a joist problem, we're told in the problem statement we want to choose a 2 by something. So that eliminates a bunch of options here. We don't want a 4 by or a 3 by or a 12 by or anything like that. We just want to limit our options. Where to go? Right here. To these sizes, a 2 by 4, a 2 by 6, 2 by 8, 2 by 10, so on. So I needed a section modulus of 15. So 2 by 8 is not quite going to get the job done. It only has a section modulus of 13.1. So if I bump that up to a 2 by 10, that has a section modulus of 21.4. So I think that's where we'll start. We'll use that as our starting point. So our first trial timber is a 2 by 10, which has a section modulus of 21.4. Now, the problem statement from the book, I don't think specifically said anything about checking deflection, but you will need to check deflection on the test, so I'm going to include that. So that means we're going to need to take into consideration what the moment of inertia is, which is going to give the joist its resistance to deflection. So for a 2 by 10, a 2 by 10 has a moment of inertia of 98.9 inches to the fourth. For resisting shear, we need to look at the area of a 2 by 10. The area of a 2 by 10 is 13.9. inches squared. And we may or may not need to include the self-weight of the beam. Self-weight is less of a concern with wood because it is a fairly lightweight material, but I'm going to go ahead and write that down anyways. A 2x10, again I'm looking at the same appendix here, has a weight of 3.85 pounds per feet. Okay, so we should, if we're going to be thorough here, and we might as well be, check for additional moment caused by the self-weight of the beam. So that moment due to self-weight is WL squared over 8. The self-weight is 3.85 pounds per feet, pounds per foot, I guess, times a span length of 12 feet squared over 8, and that equals 69.3, and my units here I was using pounds and feet, so this is in pound feet. So if I want to convert that to pound inches, I multiply. For every 1 foot there are 12 inches, so multiply by 12, and that gives me 831.6 pound inches. So the additional section modulus required for the self-weight moment would be that moment, 831.6 pound inches, divided by the allowable bending stress of 1000 psi, and so that's going to be 0.8316. That's how many additional inches to the third I need in my section modulus. So if I add that, let's call that S sub x total, we need 0.8316 plus what we calculated earlier was about 15. So what we're saying is we need about 15.8, or I might even round that up to be 15.9 is the total section modulus we need. Are we providing that with our 2x10? Yes, we are. It has a section modulus of 21.4. So 15.9 is less than the 21.4 we have provided, so it is still okay with regard to bending stress. So I think that's a good stopping point right there. I'll pick it up in the next video looking at deflection and shear.